Hopefully everyone is comfortable with the idea of hypothesis testing. And if you've thought about it a little bit, you would have noticed that we have a few options for how the hypothesis test decision could be made and how it compares to what actually might be the truth behind the scenes. The hypothesis test, or with that, we're trying to make a conclusion based on our sample, but our sample could be a little off. We hope that it isn't, that it's representative, but the truth is it might not be. So what are the different things that could happen? Well, we could have the truth that the null hypothesis is true. But now when I see my sample, it might say that with some significance that we should reject that and conclude that we have evidence supporting the research hypothesis. If the null hypothesis is actually true, that is the wrong decision. So we're making an error. We call that type 1 error. So we're rejecting the null hypothesis when it's actually true. We just got something a little extreme, suggesting that there was a significant enough change, but in truth there might not have been. Or the null hypothesis could be true, and we get a sample that doesn't give us a very extreme value. And we say that it's inconclusive, meaning we don't reject the null hypothesis. The evidence isn't strong enough to reject the null hypothesis, so that was the right decision in that case. On the other hand, the research hypothesis could have been true, meaning that if I'm testing whether there has been a change in the average score or whatever after a certain treatment, then the research hypothesis should be true. So if I then take a sample and I see that it's extreme enough, based on my significance level, to reject the null hypothesis, that would then be the correct decision. But on the other hand, the research hypothesis could be true, that there has been a change, but my sample doesn't quite show strong enough evidence. So I can still conclude that it's not extreme enough. I say it's inconclusive. I don't reject the null hypothesis, but that would be a mistake because it might actually be true. So it's all a matter of what kind of sample do I get. I could get something that doesn't quite lead me to the right conclusion. So when the research hypothesis is true, there has been a change, but my conclusion based on my sample is that it's not strong enough. I don't reject the null hypothesis. That is again the wrong decision, and we call that a type 2 error. So you're going to have to memorize these, which one is which. Type 1 error, when the null hypothesis is true, but I reject it. I reject it incorrectly. A type 2 error is when I don't reject the null hypothesis, but I actually should have. I should have rejected it, but my evidence wasn't strong enough based on my hypothesis test to reject it. I say, no, it's not strong enough. I'm not going to reject it, but I actually should have. Any questions on that? So I still remember, for some reason, in my second year, having to memorize this. It just didn't seem intuitive to me for some reason. Every now and then there's something that just doesn't fit with how you're thinking as easily as the rest. This was for me. I just have to memorize which one is which one is 1 and which one is 2. So we're going to associate the letter alpha, the Greek letter, with the probability of making a type 1 error. What are my chances of making the wrong decision if the null hypothesis is true? In other words, if the null hypothesis is true, what are my chances of rejecting the null hypothesis, making the wrong decision? And beta is going to be the probability of the type 2 error. the probability that if the research hypothesis is true, what are my chances of not going with it, not rejecting the null hypothesis, making the wrong decision there? Those probabilities are not necessarily the same. Type 1 error, type 2 error. All right, any questions so far? So if I visualize my curve, let's say normal curve, as nice and symmetric as I can possibly make it. And if I just focus on a one-tailed test, let's say on the high side, I would have decided on a value. Let's suppose we decide on a significance level of, for example, 5%. Then that determines our cutoff score, so that this is 5% or 0.05. What does this mean? What is this? This means that if the null hypothesis is true, then I have this distribution, the distribution before the treatment, population 2. If the null hypothesis is true, when am I going to reject it? I'm going to reject it whenever I get something in this area over here. And by choosing a significance level, I'm really saying that I'm deciding on the chance of me rejecting the null hypothesis. That's going to happen whenever I find a value over here, but I've decided that that's 5%. So alpha is exactly that significance level value. So that's half the battle won. Type 1 error, alpha, the probability of making a type 1 error, is the same as my significance level. Whether you say 5% or 0.05, I don't really care. The standard is to say 0.05, but they're interchangeable as far as understanding goes. Any questions on that? So that one's easy. Probability of making a type 1 error, I just have to say it over and over to myself. What is a type 1 error? It's when the null hypothesis is true, but I reject it. That's whenever I get a score in here, that's going to happen. And I want that to be 5% of the time. So that was not too bad. Type 2 error, sadly, is not as easy as that. Can't have them both easy, I suppose. So what is a type 2 error again? It's when I should have rejected the null hypothesis, but I didn't. I didn't get strong enough evidence. So how do you think the null hypothesis, how do you think my probability of a type 2 error is going to change if I pick different alpha values? So this I decide on. I pick 5%, or I pick 1%. How do you think the probability of a type 2 error is going to change? What is that? If the research hypothesis is true, if I compare this with, let's say, the black one over here, let's say 10% over here, 10% alpha. Well, if I go for 10%, that means I'm going to reject the null hypothesis whenever I'm in this area over here. I'm going to reject it. 10% of the values will cause me to reject the null hypothesis. If I lower this significance level, making it more extreme, I don't want to just find any score. I want an extreme score to be to reject my null hypothesis. Well, then I'm going to not reject the null hypothesis far more often if my alpha is sitting more and more extreme. But if the research hypothesis is true, then I increase my probability of making a mistake, because the more extreme the alpha is, the smaller alpha is, the more I run the risk of not rejecting it when I actually should have. Because I'm only going to reject it for a small little tail if I make alpha too strict. And I should have maybe rejected it earlier. So a lower alpha, meaning, let's say, more extreme before I reject anything, is going to cause a higher probability of a type 2 error. Because I'm not going to reject it very often. It really has to be out there before I reject it. But the research hypothesis could be true, and I didn't reject it. That's exactly the type 2 error. So there's a balance between these two. There's a balance between these two. That's not immediately obvious. Okay, so before we're going to go back to the type 2 error in a little bit, but I first want to talk about effect size. So it might not be immediately obvious, but I want to just get sort of an intuitive understanding of what effect size is trying to say. So, let me get rid of this. My hypothesis testing is only going to say, is only going to make a decision, reject it or don't reject it. I don't know exactly if it's if the treatment, so let's suppose I have my population, I'm administering a treatment, and I want to see if it has an effect, if there has been a change in the average score, whatever the treatment is applied to, stress or whatever. If there has been a change in the mean, the population mean. Now the hypothesis test might show that yes, there has been a change, the mean is different. But if I am going to base my decision on this, and maybe administering this treatment nationwide is a big project, costs a lot of money, I need to have an indication of, yeah, there is a change, but how big is that change? Is it actually worth going nationwide and administering this treatment everywhere? If the change is really small, it might not be worth it. There is a change. That's what the hypothesis test might say. But I also want to know, how big is that change? How big is the effect of the treatment? So that is where effect size comes in. I can't just blindly follow an hypothesis test. It doesn't show me necessarily or ask clearly how big a change am I looking at. Is it worth considering this treatment? What is the effect size? So the effect size has a very simple calculation. It's simply, if I look at my attractiveness example, so I had my population 2 that didn't know anything about the person, population 1 was told something about the positive aspects of the person's personality, and then we looked at how they rated their attractiveness. And then we saw, if you refer back to that example, we saw that the sample mean that I got was 220, that differed from the 200 mean for my population. Does everyone remember the attractiveness example? So now I want to know, the hypothesis test showed that there was a difference. It's more than the mean of 200, significantly more. The effect size is simply going to be the distance between those two. How much more is it? How much more is it? What is the effect of this treatment, so to speak? That is all it's going to be. So my population 2 is my, let's say, original group of people without the treatment, without having the information of the person's personality. And now my hypothesis test wanted to see that after the treatment, has there been a shift in the population? Is there a change? Is there an increase in this case? The effect size is trying to measure how big of a change there was. That's all it is.
Would you be wanting that value in like?
Yeah, so how we actually calculate it, this is how.
Okay.
Like I'm reading your mind. Actually, this is my next slide. So we just want to standardize it because we don't want to look at just the difference between the two means, because then it's hard to compare between other studies with different size numbers. So I'm standardizing it by dividing by the population standard deviation, just to have sort of this D measure of effect size in terms of standard deviation jumps that I can use to compare between different populations, different studies. If I'm looking at two different studies to see which one should I pick, one could be referring to stress reduction. So the stress scores will have a certain size number here. Another one could be something completely different numbers. But by standardizing the difference between the two means, I can compare those two, the effect size for each one. So that's pretty common, to standardize it by way of dividing by the standard deviation. So we call this Cohen's D, measuring for the effect size. So a nice and simple calculation to see if even if there is a difference between the two means, how big of a difference is that? What is the effect of the treatment? And the hypothesis tests just say, yeah, reject, don't reject. But is it worth it? The effect size is an important statistic to note, especially in research papers. So if I look at different examples, just to sort of get us used to it, the formula is not complicated at all. What is the effect size? So this could be a good little multiple choice question. And I give you 4 different numbers. What is the effect size for the personality attractive example? So there is not the same one as what we discussed. So our population mean was 200, standard deviation of 48. So now I take a sample, I see it's 208. That is an increase, but what is the effect? I calculate this D and I get 0.17. If I have different numbers, for example, what happens to the effect size if the mean difference is 16 and the standard deviation is still 48? Then instead of 208 versus 200 difference of the means, I now get a slightly bigger gap, so the effect size will be bigger the further away the two means are from each other. But it's also affected by standard deviation. If there isn't a lot of variability in my distribution, if the standard deviation is less, then the same gap of 8 will have a bigger effect, because it's not as common to see that much variation. So the effect size is affected by both the distance between the two means as well as the standard deviation of the population in question. Any questions on effect size and the calculation? So does that sit in my big picture? Well, the hypothesis test is all good and well, but it doesn't as clearly show how much of an effect the treatment has on my population. Is it worth pursuing, or is the effect so small? Big or small, the hypothesis test is going to say, yep, reject, there is a change. But the size of the change, the effect, is something to consider.
Are you going to give us these formulas on our exams?
Do you want me to?
Yes, please. Yes.
Then I guess I will.
Thank you.
But even if I think there's some calculation that doesn't qualify as a formula I should give, if on the test you feel, oh, I'm looking for this and I can't find it, then I'll just give it to you as well. It's not It's not that big a deal. So, because what's going to happen in reality, one day you're going to maybe have to do something or read something. You're not going to be expected to know all these formulas. You just look it up. So it's the same idea. Do I understand the concepts? Not can I memorize a bunch of formulas. So no, I'm happy to give that to you. And if there's one missing, I'll just write it on the board. Not a big deal. You don't want me to? Oh, yeah. Yeah, no, it's not an exercise in memorization. Then I would fail. You have to memorize. I don't even know what I did yesterday. Well, I was 6, so that doesn't help.
With these things, if you're like reading
These things. Keep it more specific.
like D and sigma and all that.
Yeah.
If you're like reading a research article,
Yeah.
are people like
They're going to
using
say
those?
the effect size. Yeah.
So they'll say like with an effect size of this.
Or listed in the table or something. Yeah.
Okay. And do they come with like D and sigma and those like letters, or are those only used when you're calculating?
No, it depends. We'll see in a little while that we rarely know this sigma.
Yeah.
So we'll estimate it and then we'll call it S. But yeah, they'll use the D unless there's another method. There are slightly different versions, different things you can do, but this is sort of the basic one. So depending on the test, things like effect size and those formulas get really complicated very quickly. But it's still effect size, and usually a D, or there are some other ones as well. But hopefully they'll refer to effect size, and then you see, oh, okay. At least have an idea of what that means. It's a measure of how big the change is, how effective the treatment, things like that. Yeah. So effect size is fairly standard to include in papers. Okay, effect size. Let me see. The other idea. Do I know? I jump to the next one. Oh, it's not a slide. Did I miss it? Oh, okay. So, how do I interpret the number, the value of D that I get? Well, it's broken up into easy categories, small, medium, and large. Something my 3-year-old can understand. Small, large, medium. If I don't have a big gap, sure, it depends on the standard deviation as well. If I get a value around 0.2, that's considered a small effect size. If I get a value around 0.5 for D, that is considered medium. And if I get a value of 0.8, that is considered a large effect size. So between different studies, between different treatments, I can easily compare. Oh, one has a D of 0.2, the other one has a D of 0.5. So the 0.5 has a bigger effect on the population. So that, I'm not going to give it a formula. You have to know 0.2, 0.5, 0.8. Or if it's something close, 0.3, it's still fairly small. You can get something in between, maybe small to medium size. So you can combine these depending on where your number sits. 0.2, 0.5, and 0.8, small, medium, and large. So some things I do have to memorize. I do have to remember what is a type 1 error, what is alpha, and those things. Yeah. I'm not giving you absolutely everything, but calculation formulas I'm happy to give you.
So that includes the definitions?
Hmm?
That includes the definitions? Of the system?
So in terms of effect size, for example, this is all you get.
Yeah.
You have to know what this
Right.
means
Okay.
and this and D. Just something to help you. How do I calculate this? You can look up that. Yeah. But anything concept related, like how do I interpret this? What is D? What am I measuring here? Those things have to be. It's sort of subjective where the line is in a formula sheet, but still. The other one is statistical power. Statistical power. Related to this, but not exactly the same. I want to know how strong should I say, how strong my study or experiment is. The evidence that I got from my hypothesis test, how strong is that evidence? I know the hypothesis is going to, the test is going to say, yeah, reject the null hypothesis or don't. I want to have a measure of how strong is that evidence? What is the power? Now the idea of power is going to be a little bit more complicated than the effect size, but I think we can handle it. I think we can handle it. That's too big. So there's multiple ways of explaining the idea of power. You can really use whatever sentence feels the best to you. So definition 1, let's see if that makes sense. The probability that a study will produce a statistically significant result when the research hypothesis is true. So I want to know, if I'm supposed to reject the null hypothesis, what are my chances of actually doing that? What are my chances of actually doing that? Well, if I go back here to the very first slide, we still have to say something about the type 2 error. This is our significance level. There's nothing to this one really. I decide on that alpha. We haven't really talked about the other one yet. So a type 2 error is when the research hypothesis is true. I'm supposed to reject it, but I don't. That's a mistake. The power is related to, the power is going to be my chances of getting this square over here. If the research hypothesis is true, what are my chances of making the right decision? Correctly rejecting the null hypothesis when I should. So the power is going to be the probability of landing me in this square over here. The type 2 error is going to be the opposite of that. So let me put it this way. So let's say here, given, that's supposed to be E, given that the research hypothesis is true, let's say it like this, I could either reject the null hypothesis, and the probability of that, plus the probability that I don't reject the null hypothesis. What is that going to be? When those are my only two choices. 100%. It's going to be one of them. If I don't reject the null hypothesis, this is the probability of a type 2 error, which is called beta. This is the power. So together, they're going to equal 100% or 1, depending if I look at decimals or percentages. Together, they are 100%. So if I look at the power and try and find a number here, that will give me the probability of a type 2 error, that I should have rejected the null hypothesis, but I didn't. So these two are linked to each other in a simple way. So the statistical power, the power of the study with the evidence from my sample, is exactly this. It's the probability that the null hypothesis is rejected, but it shouldn't. But it should have been. The research hypothesis is true, and I correctly reject the null hypothesis. Another way of saying it is the probability that you will not make a type 2 error. It's the other side of this. Either I make a type 2 error or I don't. Together they're 100%. The power is the probability that I don't make that kind of error. Does that make sense a little bit? We've done the type 1 error. We have to explore the type 2 error, and the way to do that is by way of this idea of power. So the power of the study is going to tell me, because of this link, what are my chances of making the wrong decision? This kind of decision, where I want to reject it, but I don't. I don't want that to be too high. Too high. And this is affected by things like sample size and the effect size as well. So often by doing a preliminary study, you can get an idea of the power, and then you can calculate, well, I don't want this to be too big. If my power is small, that means this is big, because they add up to 100. If this is small, then this guy is big. If this power is big, then that one will be small. So if I do a preliminary study with just a little focus group perhaps, administer the treatment, see what happens, and I get an idea of the power and the effect size and all those things, I can determine how much bigger do I need my sample size to be to lower this type 2 error.
So it should
That's
have
all a little vague right now, I know, but just to get the idea that they're in balance. We are going to see how to calculate this, and that gives me an indication of the chances that I'm going to make this mistake. And if this guy is big, then I have very little confidence in what I'm doing. Because if there's a very high probability that I'm going to make the wrong decision, then I'm not very confident in what I'm doing. Sorry, yes?
I'm sorry. So it should be 50-50?
The standard here is to have this around 20% or less.
Okay.
In other words, we want the power to be at least 0.8 or 80%.
Oh, sure.
Just like alpha is sort of, depending on the study, I guess there are some extreme cases, no higher than 5%. That's sort of the standard alpha. This guy sort of has this general agreed upon rule that we don't want this to be too high. So sort of a general rule, we want power to be at least 0.8 or 80%. Better, of course, higher is better, because that means my chances of making type 2 errors even less, but once it gets lower than that, then it's not very good. So that's sort of the standard that I'm aiming for. And we'll see that by taking bigger and bigger samples, I can increase the power, and thereby decreasing my risk of making that error. Okay, 6.5. So just to get an idea now, it's related to the type 2 error probability by having a stronger experiment, stronger treatment, I'm lowering my chances of making the wrong decision. Now, how do I calculate power? How do I calculate power? So let's go back to our personality attractiveness example. And just see the calculation first, and then we can look at which aspects affect this number, this power, and thereby this probability of making a type 2 error. Okay, so my personality attractiveness example, we're fairly familiar with that now. So I have my population mean is 200. If I look at the distribution of means that I'm using in my hypothesis test, remember we looked at the distribution of means because my sample is more than just one value. So the sample mean, where does that sit among all possible means? The distribution of means has the same as the population mean, but the standard deviation of that distribution, I call that the standard error of the mean, that was a little less, sigma over root n. And then for this example, let's suppose we take our sample average, and we see that it's 208. That is more, but how significant is that? How powerful is this study? Is it a big increase or not really? So what we do then, so I'll take this 208 from my sample as the predicted mean of the new population. So let's get a sketch here, since that's only going to be on the second slide. So I'm trying to see with the hypothesis test whether or not there has been an increase in a change in the population. So my sample mean is going to be used as the new, slightly increased population mean. So if I do that over here, this will be the distribution of means. So here I have my mu m, and I decided on 0.05 alpha, one tail. I'm trying to see if there's an increase. So let's suppose that's over here, so that this area over here is alpha, which is 0.05, 5%. So if I get something extreme enough, my hypothesis test is going to conclude that there has been an increase, and I should reject the null hypothesis. All right. What was the z-score there? It was 1.64. Now I want to know what is the corresponding x value. What is the corresponding rating at this point? So I use my formula to go from a z-score back to the raw x value for this distribution of means, and I see that's at 209.84. So I'll just write here x corresponds to 209.84. So our hypothesis test usually compares the z-score values, but I could also have found the cutoff, then see what is the score that actually that this 1.64 refers to, and then compare that to what I see in my sample of 208. So in this case, if I have a 208 sample average, sample mean, that's not extreme enough, because the 209.84 is the cutoff. So I have a sample average that sits over here to the left. So if that is the case, do I reject the null hypothesis or not? It's not exactly the same as our original example, which had a 220 here. Let's suppose I got a 208. What is the conclusion from the hypothesis test? Yeah, it's not extreme enough, it's not strong enough. It's inconclusive, so I don't reject the null hypothesis. Based on the evidence that this sample gives me, I can't say that there has been a significant enough change. All right? So now I want to calculate the probability that I don't reject the null hypothesis, but I actually should have. So in this case, I don't reject the null hypothesis. But what is the probability that I actually should have rejected it? If the research hypothesis is true and there was an increase, I didn't reject it. What is the probability of a type 2 error? This is what the power is going to tell me. So I'll zoom in on that sketch in a second. It's surprisingly small. So I've got the 209, and now I want to calculate the z-score for this point, but on the distribution of means for the population that receives the experiment. So let me put it over here. So this mean is the sample mean that I'll take, that's my 208, 208 sample mean, and that's what I'm going to take as the mean for my shifted new population, population 1. So I'll put that over here somewhere. Try to make the sketch as good as their sketch. We'll see. Probably not going to be as good. Oh, that's not very balanced, is it? Let's try that again. When I want to have it nice and symmetric, it's not going to be. So here's my mu predicted. That's the 208. So there might have been, the research hypothesis could have been true, and there is a shift in the population after the treatment. And I'll take my sample mean to be the mean of that population, population 1. All right, so then I want to know on this guy, on this shifted population, so to speak, where does this 209 put me? How far away from this mean is it? So let me just shift this so I can extend my line here. So that is 208, the sample mean that I'm using as that's the best prediction I have for the changed mean for my new population. I want to know what is the z-score here in this slightly shifted distribution. So I can calculate that as the 209 minus this top mean, which is 208, same standard deviation, and I get a 0.31. 0.31. Okay? So let me zoom in here first and then go to number 4 in more detail. How big can I make this? Slightly, we'll leave the top out there. Like that, okay. So, just trying to get the idea. I'm going to go too fast. I know it's a little blurry. So, maybe let's average by 1. That's a little better. So the bottom is my population 2, which is before the treatment, so to speak. Population 1 is with the treatment. So population 2 had the mean of 200, and I decided on my alpha of 5%. That gave me my cutoff, which was a z-score of 1.64. That corresponded to an actual rating score of 209.84. Now, if the research hypothesis is true, then there was an increase, and it did change to an increased mean, which I don't know exactly what it is. So I'm going to use my sample mean of 208 to predict that new shifted population mean. Where does this cutoff value now sit in this distribution? 209, I follow it up. It sits over here, just to the right of 208. A z-score of 0.31, so more or less a third of a standard deviation step in this distribution. So now, what is a type 2 error? The type 2 error, make this line solid, is when the research hypothesis is true and this shift is actually what happened, but I don't reject the null hypothesis. When do I reject the null hypothesis? When I'm over here to the right of this line. So I don't reject the null hypothesis whenever I'm in here. Whenever I'm in here, I don't reject it. So for all of this, I'm not going to reject the null hypothesis. So that is going to be the probability of making a type 2 error. Oops, type 2 error. There was a shift. I should have rejected it, but for all of these values, I won't actually reject it because they fall to the left of my cutoff value. And then the other side is the power. Okay, so in this case, I have a Z value of 0.31 in this distribution, which has a mean, let's call it predicted, still distribution of means, but a shifted one, 208. Standard deviation is still the same, whatever it was. I want to say 48, but I can't remember. Where does the Z-score sit? Over here. So I go to my table, I look for the percentage in the tail corresponding to a 0.31, and I get 37%. Highlight the calculation. So now, using my table for a Z-score of 0.31, I can calculate many different ways depending on how it sits. I can see it as a table, in the table. I can see it as the tail. I can see it as the percentage to the mean, and combine different regions, and I get a 37.38% for the power, which then gives me the probability here of 62.6117. No, these should add up to 100. Did they do this right? That does not look right. Shouldn't it be 62? No? Yes? Maybe a little typo there? Typo there. They should add up to 100. The probability of type 2 error is 100% away from, or 100% the difference between that and the power. Together they make 100%. Yes?
I'm confused with how you got the power.
The power is, let me put it in red, is this region. Together they make everything, these two.
Yeah.
So then I go to my table and I look up the Z score and I find the tail percentage, 37.3.
Okay.
And you said that the standard practice is 80%?
We want that to be at least 80% power.
So then that usually
So that means I want the probability of making this type of error to be less than 20%. 20% is still a lot.
So that you have to go with a significance level of 1% then?
So there are a couple of things that would affect the power. We can see from this, and I think I'm going to go through them in a second, but regardless. What happens if you lower this alpha and require something more extreme? Then this line here shifts outward, and my power is going to get less,
Yeah.
which is even worse. So I would have to be more conservative, or is conservative? More relaxed, let's say, on the alpha. Shift this to the left, and then the red will increase and the purple will decrease. But then I run the risk of making that error. So just adjusting one for the sake of the other, yes, there is a balance, but I could have the result that no, both of them are bad. At least this way, one of them's bad and the other, one of them's good and the other one's terrible. So if I did do this, I have over 60% chance of making the wrong decision. If there actually was a significant change, no, not significant. According to this, it's not significant enough. But if there actually was an increase in the scores, I'm not going to find it significant enough, and I'm going to make the wrong decision 60% of the time, which doesn't fill me with a lot of confidence. Okay. There are ways to adjust it, and to me the obvious one is changing the sample size. But let's see. So is everyone at least happy with the basic calculation? So this would be a long answer question. I want to ask, what is the power? There are 4 choices in a little multiple choice question. That's not very fair, because there's a lot to do to find that. But I find that making the graph, or 2 of them, having some visualization of what's happening, is for me the key to success. Otherwise, I have to see this in my head. There's a lot of stuff happening in my head, bats flying around and stuff. There's no space for these things. Putting it on paper, much better. So let's do another one just to make sure, because this is not the simplest thing ever. Not the simplest thing ever. Okay, so for my stress reduction example, can I zoom in a touch? Yes. What was the stress reduction example? There I administered some treatment, some stress reduction method, and I wanted to see if it's actually lowering the stress significantly. Now there is, get rid of this as much as possible. There is a sketch at the bottom, but let's see if we can come up with it on our own and how it compares to the one they have here at the bottom, which is hard to see. So what I got was that in general, before the stress treatment, the mean was 40, and I had a population standard deviation where when I look at the distribution of means, I got a standard error of 2.24. And then when I look at my sample, it did give me a lower average. It gave me a 34. But now let's see. We could accept it or reject the null hypothesis depending on where this sits. But I want to know by way of the power, what are my chances of making the wrong decision? Okay, so what were the steps? There are only 4 steps, not that bad. First step is really not much. So I want to look at my population 1 distribution of means. Sorry. Population 2 is before the treatment, population 1 is after the treatment. Population 2, the original, which was a 40 here. And yeah, I got my standard deviation. Sure, let's put it over here. 2.24. Try to visualize. If I can visualize what's happening here, the calculation becomes much easier. So in this case, let's use 1% alpha. So the probability of making a type 1 error is nice and low, or I want it to be nice and low. Let's see what happens to a type 2 error. So for, now I'm looking on this side, so maybe I'll shift this guy to the other side. 2.24. So I'm not going to put it that far, I'm just going to put it over here somewhere. That's my cutoff, so that this little region here is 0.01, and that's alpha. So that gives me a z-score here of negative. When I look it up, negative 2.33, way out there. I want to be nice and extreme before rejecting the null hypothesis. What is the corresponding rating corresponding to this z-score? I will cut off x value using the standard deviation of this distribution and the mean. I get 34.78. 34.78. So now I'm going to use my sample mean as the predicted mean of the shifted population if the research hypothesis is true and there has been a decrease. Then the distribution is shifted to a lower, with a lower mean, shifted to the left. 34 is going to sit, 34? Yeah. I was going to sit over here a little bit. close, but so I'll have a distribution that's centered like that. Well, that's nice. Little angle, but still. Where does, so I'm looking at a cutoff value of 34.78. So if I got a 34, which I did from my sample, what would the hypothesis test conclusion be? I'm going to reject the null hypothesis in favor of the research hypothesis. The evidence is significant enough with this alpha. So now let's see, so this is my predicted mean of 34 over here. This line, oh, a little wobbly. 34.78. So what do I do next? I want to see how this cutoff value, how it sits in relation to my lowered mean. So what is the z-score here? So now I have a mu, I don't want to write it up there, sorry. That is my mu, let's call it predicted. And my standard deviation is still 2.24. So using these two guys, what is the z-score? Telling me how far that is away. It's going to be, so 34.78 minus the predicted mean over the standard deviation, 0.35. So again, it puts me very close here, 0.35. And now I can look up in my table. Let's go with the same colors we did last time. Look up in my table and look at the tail here. And I would get a percentage of, oh, let's scroll down a little bit. I would get a percentage of 13.68. That right?
Just happy it's under 20.
Well, that's the power.
Oh.
Because I'm going to reject to the left of this cutoff, and I'm not going to reject to the right.
Yes.
So, oh, no. You're right. Because it's swapped around. It's the left side. So my red's wrong. Sorry. No. Let's just talk through this again. Everything's shifted. Last time we had the right tail, now we have the left. So let's talk through this and make sure. Reconstruct my curve here. So, okay. Which side is which? I'm going to reject the null hypothesis if I'm to the left of this cutoff. I'm not going to reject the null hypothesis if I'm to the right. A type 2 error is what?
Saying it's inconclusive when...
So if I'm on the right, when this actually occurred, that is a type 2 error, and that was purple. Was it purple? No. So that is type 2 error. And the red is going to be the other side, where I reject the null hypothesis when I should have rejected the null hypothesis. So that would then be the power. Okay? Does that make sense? So depending on which side I am, it's going to flip around. So the best way for me is to talk through it. And based on my understanding, I can figure out which side is which. I think that's the safer way than memorizing. So I get, because this is the tail, here's the center, 34. This separation line is sort of to the right of that, so I can use the table and find the tail value. I just need one of them. It doesn't really matter which one. They do what? They do it in a different way. they look at the percentage mean to Z, so they get this little gap here to be 13.68. I don't have my book with me, so if someone could verify these numbers, that would be lovely.
I don't know why they do that, isn't it just easier?
No, I don't either,
Yeah.
honestly. With the Z.35 is in the book, so what do we find for the tail? Can someone look that up?
36.
36 exactly?
No, it's 36.
0.32? Okay, that is right. 36.32. No. I say one thing, but I write another. Okay, so I really don't know why they bother with this. Maybe their tables. So then I just need to find one, right? So this is definitely the right tail, so it fits nicely with the table. And then that is my probability of a type 2 error, and then the power will simply be 63.68, which is what they find this time. Okay. So this one is much better, yes. Your yay was justified. It's not quite as good as I was hoping, because I'm hoping for an 80%, 20% split, or better, but it's better than the previous one, for sure. Any questions on the idea or the steps? I'm looking at if the research hypothesis is true, and this shift occurred, what is the probability that I'm still making the wrong decision? And what is the probability that I'm making the right decision? So I want this to be at least 80%. There's always going to be a risk. There's always going to be a risk. So in this case, you could argue, well, this 1% is really tight. Do I really need it to be that tight? If I shift this a little bit to 5%, then this decreases. Maybe I get 5% and 20%. Maybe I get them both. So there's a balance between these two for sure. So what influences the power? Well, one is the effect size, which is an indication of how big the shift is. How big a difference did I see from before the treatment to after the treatment. So if I have a larger effect size, then this shift is going to be more, and this line is still the cutoff. The cutoff line might be the same, so this is just going to shift more to the left, and thereby decreasing the probability of making a type 2 error. So by way of a preliminary study, you can have an estimate of the effect size. Maybe you take just a small little focus group, a small sample, have an idea of the predicted mean, see the difference between them, the effect size, and you can have an idea of what kind of power you're looking at before you do the full study. So on the one hand, effect size, which is directly related to the distance between these two, how much the treatment has affected the population. So that's one, just the amount of shift, so to speak. The other one is the sample size itself. So if I look at this, for example, the distribution of means, the personality, and the attractiveness example again. No distribution, significance cutoff for 5% alpha. In this example, A is the predicted distribution with a median effect size. This is the same as effect size. And my sample size was, I want to say 64. Was it 64? I think so. 64 sample size. Now, what is going to happen to this distribution if I increase the sample size? I really just want to think about this. And that's really all I want to say, to be perfectly honest. Let's go back to a simpler sketch. Let's go back to this. I like this one the best. What is going to happen to my distribution of means if I can increase the sample size? If I do this again, but for a larger sample, what is going to happen to this guy? What's going to happen to this guy? So what happens if n increases? If I do it again, but for a larger sample, what's going to happen? The mean might stay the same. Well, the mean is going to stay the same. This is the population mean, for which I know the distribution of. What is going to happen to the standard deviation of the distribution of means? It's going to get smaller because this guy is sigma over square root of n. So that means if I'm increasing the sample size n, I'm dividing by a bigger and bigger number. Even though I take the square root, if n gets bigger, this denominator is going to get bigger as well. So this is going to get smaller. So that is going to get smaller and smaller. Now visually, what is the effect if that gets smaller and smaller? There's going to be less variation. Everything's going to get thin and packed close to the mean, like this little exaggerated distribution. Everything's going to get nice and thin because there isn't much variation. So if I see the same effect size in terms of the difference between the two means, but they're all very, very thin, very slim. What color can I use to illustrate this? They're all very thin around here. This is all going to be thin because I'm assuming the same distribution. See, the overlap is going to be much less than when the standard deviation was bigger. So by increasing the sample size, I'm directly affecting the standard deviation, the variability here, which is going to give me a much better power, because this line isn't going to be, this line, for small standard deviation, this line is going to sit somewhere over here. The tail is going to be small very, very earlier, much earlier. So if I follow this up, I'm exaggerating of course, but you see you don't have as much of the type 2 error region as you would have previously. So one way, or a first way to try and increase the power, decreasing the probability of a type 2 error, is by looking at a larger sample. Larger sample decreases variability in my distribution, and the overlap is not going to be as big. And the type 2 error here is really dependent on the overlap. Does that make sense? So I just wanted to sort of have an understanding of what is the effect of the sample size on the power, and therefore the probability of a type 2 error. So I can stick to my alpha. One option is to make the alpha a little bit more relaxed, and that is going to help me with my type 2 error, my power. But if I want to stick to my alpha, I can't just make this too big. Something that I could do is look at a bigger sample size. And there are ways to calculate it with software or tables you can look up. Given a target power value, it can give me, given a target power value and an estimated effect size, by a preliminary study, I can get an idea of how much this is going to shift by. I have my desired power value. I have alpha, of course, that I decide on. Those are the things I need, and I can calculate sort of a minimum sample size that I would need to get that desired alpha. Now it's a little bit too complicated to do by hand, but all the factors are there. Just as I use the sample size and therefore the standard deviation and the mean, I get a predicted mean, I calculate the power. I can sort of do that in reverse. Given the power that I'm looking for, at least 80%, let's say, what is the sample size that would give me that? And there are online calculators to do that. It's a little bit too much that I don't want to do it by hand, but it's just essentially the reverse of the process that we've done by hand. Yes?
I understand how there's less variation with a bigger sample size. I just don't get the part where you're talking about no more overlap or less overlap.
Because my tails aren't as wide,
Mm-hmm.
but the distance that it shifts is the same. If I'm only changing, the variability, the effect size is the same. Well, in terms of the distance between these two.
Yeah.
So I'm going to shift by the same, but they're thinner. So I'm going to shift it, and the overlap, they drop off very quickly in the purple ones. So if I shift by the same, there may be little bits of the tail overlapping. The tails aren't as big anymore.
So you're moving your Z cutoff.
Because I'm shifting it by the same amount.
So what does that mean?
It means that the purple area is going to shrink, which is the type 2 error is going to be much lower.
Oh,
And the power is going to be better.
so you do this when you want it that way.
Because if I look at my preliminary study, let's suppose this is, the alpha, I'm good with alpha, this is 1%, this is good. But my type 2 error is way too big. I need it to be at lower than 20%, ideally. Less is of course better, but this is too much. 20% is sort of, I don't want to go over that. So what can I do if I don't want to relax this? What else can I do? Well, what I could do is make this distribution thinner. In other words, decrease the variability. How can I do that? Because the population variance is what it is. By taking a bigger sample, I affect the standard deviation of this distribution of means. Making it thinner with the same shift, the overlap is going to be much less.
Okay.
So instead of calculating these things, what am I going to do in practice? I'm not going to calculate this by hand with target n. There are ways to do that easily with software, online calculators. So I'm just doing the forward calculation by hand, and then just trying to get an intuitive understanding of how can I improve the power. If my calculation shows, oh, power is really not good, what can I do to improve that? If I don't want to adjust the alpha, what else can I do? Well, the main one is the sample size. And I can calculate what is the minimum sample size I need to get to where I want to be.
So intuitively, if research hypothesis is true, and your sample size, approaches infinity, then your type 2 error will decrease.
Yes.
Because they're different.
All the way until I'm essentially, well, there's a limit to how big my sample can be.
But if you
financially, there's a limit.
If you administered your therapy or whatever the experiment thing on the entire population in Canada, so n equals 30 million, so then
Then there is no variation. So if n goes up indefinitely, this is going to shrink to 0 until I have the whole population. Then there is nothing. There is no variability because I considered everyone. But that's not practical. There's a middle ground. But with your calculation, you can see, okay, I need an n of 1,000. Is that practical? Can we do that? And if we can't, how close can we get? Can we relax this a little bit? How close can we get? So there's a balance when it comes to actually implementing the study. But theoretically, we can calculate, I want the power of, let's say, 80%. What should the sample size be? So based on this, if everything else stays the same, my sample size was, what was it? 60 something, yeah? That's clearly not enough. Now you can experiment and just try one, but you don't want to implement that if it's still not going to be correct. So I want to do the calculation in reverse to see, okay, maybe I need 150. If I do that, given this doesn't change a lot, then I'm going to decrease the time to error. So I want to build in a little bit of margin because I could increase the sample size and this 34 could be a little bit different because it's just a sample. I could get a 35 or a 33. So I want to have a little bit of a buffer just to compensate for little variations that I could get in my sample. Just the idea that I want to get across, how sample size makes a big difference in my accuracy and the accuracy with which I can use my hypothesis test to make a decision. Makes sense. So I don't want to get caught up in the detail, that's why we do one calculation, and then visually I just want to see and understand how are these things related. How are these things related?